Welcome back, guys. The last video got cut off while I was trying to explain this. So we're going to start this video by going through this again. Then we're going to talk about the chain rule for a function of n variables, where x sub 1 is a function of t, x sub 2 is a function of t, and x sub n is a function of t. So I can think of these as the parametric equations of some vector valued function r of t. So we'll talk about that. And then we're also going to look at the chain rule when you've got two independent variables. So in the last video, all of our x's and y's and x's, y's, and z's and x sub 1s through x sub n's, those were all replaced by functions of t, a single variable. And now we're going to replace the x, the y, the z, x sub 1 through x sub n with functions of s and t. So these are going to result in functions of two variables. So this one is like taking this function of x and y, and instead of writing it in terms of x and y, through a substitution, we're going to write it in terms of two new variables, s and t. And this is similar. Instead of writing everything in terms of x, y, and z, we're going to write it in terms of two new variables, s and t. And the last one is also similar. We've got n variables here, and we're going to replace them all with functions of s and t. So when we're done, w will depend on s and t only. The x sub 1 through x sub n will be gone because they will have been substituted. So this is what we were talking about at the end of the last video. If you have w, and w is a function of three variables, x, y, and z, and x is being replaced by x of t, y is given by y of t, and z is given by z of t. So we might think of these as positions as functions of time. If my x, y, and z are changing with time, if those positions are changing with time, then we can think of w as changing with time as well, at least from the perspective of some particle moving along this path. Well, according to our chain rule, the change in w with respect to time is this plus this plus this. It's the change in w with respect to time due to changes in x, plus the change in w with respect to time due to changes in y, plus the change in w with respect to time due to changes in z. Now, when I see a function of three variables, I know my chain rule is going to have three terms. If this had four variables, I know this would have four terms. If it only had two variables, I know this chain rule would have two terms. But I can always write that more compactly using the gradient and a vector valued function r of t. So if I put these guys together, if I think of this as an x, y, and z that are the components of some function r of t. So maybe this is the position of some object in three-dimensional space as a function of time. Well, if I want the change in this function with respect to time, I take the gradient of w, or the gradient of f, same thing. So it's the vector of first partials of w, and I dot that with x prime, y prime, z prime. So I'm thinking of this as a dot product now. And when I think of it as a dot product, I've got these three guys, and I'm multiplying by these three guys, and then I add. Well, then I see when I put those first three factors together and make them components of a vector, that's the gradient of w, or f, if w is f of x, y, and z. It's the gradient of f, but then we want that evaluated at x of t, y of t, and z of t, so that this is a function of t only. And then this guy, let's just x prime, y prime, z prime. Well, if this is our position vector, that's velocity. So we're taking this gradient and we're dotting it with the velocity vector. And that's giving us the change in w with respect to time. Okay, that's if we have a single independent variable. That's if x, y, and z all depend on t. You can imagine how this changes for this one. It really doesn't change very much at all. The only difference between the chain rule for this one and the chain rule for this one is that instead of having an x of t, y of t, z of t here, you're going to have x sub 1 of t, x sub 2 of t, x sub 3 of t, all the way through x sub n of t evaluated here, dotted with r prime, where r prime is a vector valued function with n components. So the fact that there are n variables here really doesn't change things very much at all. Just means a little bit more computation. But if I think of this as r of t, so I'm replacing this with the component functions of some position vector r of t, then dw dt is just given by this formula right here. Okay, that's the same formula that I would use in this case. Now let's look at the chain rule with two independent variables. If f depends on two variables x and y, and I replace x with x of t, or x of s and t, and I replace y with y of s and t, the new function will depend entirely on s and t. So it doesn't make sense to take a derivative of this with just respect to t now because it has two variables. So I can think of this as a function of two new variables, s and t, so I can compute two partial derivatives of this new function. I can take the partial of z with respect to s and the partial of z with respect to t. And the same is true here. If w depends on x, y, and z, and x, y, and z all depend on s and t, we can put all of that together. Excuse me, I replace x with x of s and t. I replace y with y of s and t, and I replace z with z of s and t. And the pattern continues. If you replace x1 through x sub n with all these functions of s and t, then you're going to end up with a new function that depends entirely on s and t and not these n variables x sub 1 through x sub n anymore. Okay, and so we can talk about the partials of this function, z with respect to s and t. After I replace the x, y's, and z's with functions of s and t, I can talk about the partials of w with respect to s and t. And the same would be true here. This is because we have two independent variables, s and t. And you might say, why on earth would I ever do that? Actually, we've done this before. Anytime you've ever changed from rectangular to polar coordinates, you've done this. So you said, instead of thinking of this as a function involving x and y, why don't I think of this as a function involving r and theta? R and theta might be a more elegant way to describe the same thing if you're dealing with part of a circle or something like that. So this change of variables, even though it seems like sort of arbitrary and unnecessary, it's something that might be very convenient for us to do sometimes. There might be a certain set of variables that illuminates some part of the function, that makes something about the function very clear, that wouldn't be clear in terms of x and y, or x, y, and z, or x sub 1 through x sub n. And then we might want to know, well, after I make that change of variables, how does the old function change as the new variables change? And the chain rule would be able to tell us that, it would be able to describe those changes for us, those instantaneous rates of change. So let's look at a simple example. Here is my w. It depends on two variables, and x depends on s and t, and y depends on s and t. Well, we have three different ways that we can handle this. The first way is to just substitute. So you replace x with x of s and t, and you replace y with y of s and t. So my w is x squared minus 2 times x times y plus y squared, and x is s plus t, and y is s minus t. And so after the substitution, w depends only on s and t. So you can do some algebra, write this twice in FOIL. Got a negative 2 here. s plus t times s minus t. First times first is s squared, outer times outer is minus st, inner times inner is plus st, so those reduce. And last times last is negative t squared. And then I've got s minus t times s minus t over here. Keep going. Over here we'll distribute. First times first is s squared. Outer times outer is ts. Inner times inner is another ts, or st, I guess. We've got two of them. Last times last is t squared. Distribute the negative 2 here. Negative times a negative makes that a positive t squared. And then over here, when we FOIL, first times first is that, outer times outer is minus st, inner times inner is the same, last times last is t squared. And then we see if anything reduces. I've got 2st minus 2st, so those are gone. S squared and s squared minus 2s squared. Those are gone. And now I've got t squared, 2t squared, and another t squared, so that's 4t squared. So that's my w. And the derivative, partial derivative w with respect to s. Well, there's no s's in that, so we get 0. And the partial of w with respect to t is just 8t. Okay, so that's the first method for finding the partials of w with respect to s and t. It's probably the simplest, but we may also want to illustrate the chain rule using this w. So we'll use the chain rule. For the partial of w with respect to s and the partial of w with respect to t. Now w depended on two variables, so each of these partial derivatives is going to have two terms. So you can write it this way. Partial of w with respect to s is partial of w with respect to x, that was one of our original variables, times the partial of x with respect to s. Notice that these variables match. So this is giving me the change in w as s changes, as x changes. Now if y is also changing, we get a change in w with respect to y times the partial of w, or times the partial of y with respect to s. Notice that those variables match. These two match here, these two match here. So this is giving me one part of the change in w, this is giving me the other part of the change in w. We add them together, we get the total change in w with respect to s, holding t constant. Or we've got the partial of w with respect to t, and it's going to look exactly the same because w depended on x and y. So we get two terms. But since this is a partial with respect to t, this is a partial of x with respect to t, and a partial of y with respect to t. These variables all match. Okay, so this is one version of this chain rule for a function of two variables. W depended on x and y, so we've got two terms. And we're going to two new variables, s and t. So in order to do this, to do either one of these, I need partials of w with respect to x and y, entirely in terms of s and t, and I need partials of x with respect to s and t, and partials of y with respect to s and t. And then we'll just put them all together in the right combinations to write down the partials of w with respect to s and t. So first things first, let's compute the partials of w with respect to x and y. Those were our original variables, but then we want to write them in terms of s and t. Okay, so w was this function. It was x squared minus 2xy plus y squared. And if we're differentiating with respect to x, I get 2x. Here I've got a constant times x. The derivative of a constant times x is just the constant. 2 and y are behaving as constants. And if y is constant, derivative of y squared is just the derivative of a constant, which is 0. So the partial of w with respect to x is this in terms of x and y, but I want them in terms of s and t. So I replace my x with whatever it was in terms of s and t, which is s plus t, and I replace my y with whatever it was in terms of s and t, which is s minus t. Distribute the 2, distribute the negative 2, and we see the 2s and the negative 2s reduce, and we just get 4t. All right. Now we want to do the same thing for the partial of w with respect to y. We take the derivative with respect to y. There's no y's in this, so the derivative of a constant is 0. This is the derivative of a constant times y. The derivative of a constant times y is just my constant. Derivative of y squared with respect to y is 2y. Now that's my answer, but I want to replace x with whatever it was in terms of s and t, and replace y with whatever it was in terms of s and t. So we'll distribute the negative 2, distribute the positive 2, the s's reduce again, and we get negative 4t. All right. Now in order to compute these partials, or to compute these derivatives, I need the derivative of x and y with respect to s, and I need the derivatives of x and y with respect to t. So x as a function of s and t was s plus t. So its partials with respect to s and t turn out to be just 1. Derivative of this with respect to s is 1 plus 0. Derivative of this with respect to t is 1 plus 0, or 0 plus 1. And y as a function of s and t was this. The derivative of that with respect to s is just 1. The derivative of that with respect to t, there's no t's there, so we just get 0 times negative 1. All right. So we have computed the partials of x with respect to s and t and the partials of y with respect to s and t. Now we just substitute into those formulas up there, and those will give us the partials of w with respect to s and t, and hopefully we get exactly the same result we got up here. The partial of w with respect to s is 0 because there's no s's here. And the partial of w with respect to t should be 8t if we've done everything correctly. Okay. So I've got all these derivatives. Keep that in mind. And now I want the partial of w with respect to s. So first I look at the change in w with respect to x, holding y constant, and then I multiply by that derivative. Then I want the partial of w with respect to y, and I multiply by this partial derivative. So I'm just substituting everything in. I always put parentheses as placeholders. Partial of w with respect to x in terms of s and t turned out to be 4t. Partial of w with respect to y in terms of s and t turned out to be negative 4t. Any derivative of x with respect to s, that was 1. And any derivative of y with respect to s, also 1. So I've got 4t minus 4t, which is 0. Hey, that's the same thing that we got over there. That's a very good sign. Okay, now let's look at the partial of w with respect to t as well. Just writing, oops, that's an x. So this is a partial of w with respect to x times the partial of x with respect to t. So this is the change in w with respect to t due to changes in x, plus the change in w with respect to t due to changes in y. Now these two partials, I already wrote those down. They're 4t and negative 4t, so I'm just using those again. And now I just need these two derivatives. Derivative of x with respect to t, which is 1. Derivative of y with respect to t, which is negative 1. So now I've got 4t plus 4t, that's 8t. Is that the same thing that we got the other way? It is! Very, very good. Okay, so you might say, all right, well that's fine. I always give you a shorthand way of saying the same thing, right? Well, this is the gradient of w dotted with partial of x with respect to s and the partial of y with respect to s. And this is the gradient of w dotted with the partial of x with respect to t and the partial of y with respect to t. You're like, what is that? Well, we haven't really talked about these yet, but we can come up with another vector-valued function. In the previous chapter, we studied vector-valued functions of t. Those give us space curves. This is a vector-valued function of s and t. Now, most of the time, this won't give us a curve. It's actually going to give us a surface. You're like, what? Yes, every xy, or every st, will be associated with an xy. And as s varies and as t varies, generally that's going to give us a surface. We call this a parametric surface. So R has parametric equations, x of s and t, y of s and t, which in this case are s plus t and s minus t. Well, that means this is just the partial of R with respect to s. And this is the partial of R with respect to t, dotted with the gradient of f evaluated at R of s and t. And then this is the gradient of f evaluated at R of s and t. So each of these rules can be rewritten as a gradient evaluated at R dotted with the appropriate partial derivative. If I want the derivative of w with respect to s, this needs to be a partial with respect to s. If I want the derivative of w with respect to t, holding the other variables constant, this needs to be the partial of r with respect to t. Okay, and that was for this guy where w depended on two variables originally, and then x and y depended on two variables. I know I used z here, but it's the same idea. I've got two variables here, and I'm mapping to two new variables, and I just did this. I just had w's instead of z's. Now we could also do the same thing if w depended on x, y, and z. We might write x, y, and z in terms of these new variables s and t. Well, that's going to be pretty much the same thing as these two rules. It's really just one rule. But if w also depends on z, we're going to have a z term here, plus the partial of w with respect to z times the partial of z with respect to s, and the partial of z with respect to t for this third one, or for this second equation, excuse me. So let's do an example like that. All right, and I picked a simple one. So w is a function of three variables. So that means each of the chain rules will have three terms. I have partial of w with respect to x, partial of w with respect to y, and since it also depends on z, a partial of w with respect to z. So that's a gradient vector. taking that gradient and I'm dotting it with another vector. Since I want derivatives with respect to s here, I want the partial of x with respect to s, and the partial of y with respect to s, and the partial of z with respect to s. So this is a gradient dotted with this vector of partials with respect to s. If I think of these three equations as parametric equations of some vector valued function r of s and t, this is the partial of r with respect to s. I treat t as a constant and I differentiate each component with respect to s. So this is the gradient of w, which is f, evaluated at r of s and t, dotted with the partial of r with respect to s. Or you could use this version, that's fine too, if you prefer it. Now if I want the partial of w with respect to t, I need to take the gradient and I dot it with this vector of partial of x with respect to t, partial of y with respect to t, partial of z with respect to t. And all of these are partial derivatives because x and y and z all depend on s and t. So I'm thinking of this again as a gradient. Oops, slightly different notation. I'm using Leibniz notation and subscript notation interchangeably because they are interchangeable. And these are x, y, and z, and we're taking derivatives with respect to t this time. Well, that's just taking the components of r and taking the derivative of each component with respect to t, holding s constant. So this is the partial of r with respect to t. And this is the gradient of f evaluated at r of s and t. Okay. So this is our chain rule for two new independent variables, s and t, when the original function had three independent variables, x, y, and z. Okay, if I want to use these formulas, I need partials of x, the partial of w with respect to x, y, and z, all in terms of s and t, and then I need these partials of x, y, and z with respect to s and t. I can also just substitute and take the derivative from there. So let's use the simple method first, see what the answer is supposed to be, and then we'll use the chain rules to confirm and show that we get the same answer either way. So method number one is just to substitute. Into our equation, and then take derivatives with respect to s and t. So w is x squared plus y squared plus z squared, and x is t sine of s, y is t cosine of s, and z is s t squared. Now this is a product. If you have a times b and you're squaring it, you square each factor separately when you're simplifying. So I'll square the t and I'll square the sine of s. So this is t squared sine squared s. And here I'll square the t and the cosine. So I have t squared cosine squared s. And here I've got an s and I'm squaring it. And then t squared squared, that's this property. Multiply the exponents. T squared squared, that's t to the fourth. That's right there. Now this simplifies even further because these two have a t squared in common. I can factor that out. T squared times sine squared s gives me my first term, and t squared times cosine squared s gives me my second term. And this is equal to 1, so w is t squared plus s squared t to the fourth. All right, now that's pretty simple. I can take its derivatives with respect to s and t, and it'll be very easy to compute. So I'm taking the derivative with respect to s of t squared s squared times t to the fourth, t squared plus s squared times t to the fourth. There are no s's here. The derivative of a constant with respect to s is just 0, so that's gone. Here t to the fourth is a constant, so I can bring it down, and I multiply by the derivative of s squared with respect to s, So I get 2s times t to the fourth. That's my partial of w with respect to s. Now the partial of w with respect to t, you just take the derivative term by term. You get derivative of t squared is 2t. S squared is a constant, so I bring it down. Derivative of t to the fourth is 4t cubed. And you could factor out a 2t if you prefer, but you don't have to. So we know these are the answers that we're looking for. That's the first method. Now let's verify that we get exactly the same answers using the chain rule. So first we need to compute those partials. W depended on x, y, and z, so we need partials of w with respect to x, y, and z, and we want those in terms of the new variables, s and t. Well, w is actually a very simple function. It's just x squared plus y squared plus z squared. Simple makes it sound insulting. It's a very elegant function. It doesn't need much. Derivative of w with respect to x is 2x. Derivative of w with respect to y, treating x and z as constants, is 2y. Partial of w with respect to z, it's 0 plus 0 plus 2z. So those are my partials. Easy enough. I want them in terms of s and t. So I replace my x with whatever it was in terms of s and t. I replace my y with whatever it was, and I replace my z with whatever it was. X was t sine of s. Y was t cosine of s. And z was s t squared. Okay, and now we want, in order to use our chain rules, we need partials of x, y, and z with respect to s and t, all three of them. Then once we've got those partials, we can substitute and compute the partials of w with respect to s and t. So x was t times sine of s. So the partial of x with respect to s, well, t is a constant. Derivative of a constant times sine of s is going to be that constant times cosine of s with respect to s. And if t is our variable and s is a constant, this is just a constant times t, so we just get the constant sine of s back. Y is similar. When I take the derivative of y with respect to s, t is a constant. Derivative of cosine of s is negative sine of s. Here I've got cosine of s times t. The derivative of a constant times t is just the constant. And here my z is st squared. The derivative of z with respect to s, that's a constant times s, so we just get the constant. Partial of z with respect to t S is a constant, derivative of t squared is 2t. Okay, so we've got all of those partials. And now we're just going to substitute them into the formulas to get the partials of w with respect to s and t. I've already used this piece of paper for something else. I'm just sort of getting that piece out of sight. And there's the rules. So I'll write down my rules. Partial of w with respect to s. It's the partial of w with respect to x times the partial of x with respect to s, plus the partial of w with respect to y times the partial of y with respect to s, plus the partial of w with respect to z times the partial of z with respect to s. And we just substitute all those 6 pieces in and simplify. Now, if you haven't written any of those in terms of s yet, if you still have x's, y's, or z's, you need to substitute those. Okay, now we already calculated these. Partial of x, or of w with respect to x, is 2t sine of s. Partial of w with respect to y is 2t cosine of s. Partial of w with respect to z is 2s t squared. And then these other partials, partial of x with respect to s, y, and z with respect to s, are right here. So I've got t cosine of s here. Here is negative t sine of s for the partial of w with or y with respect to s. And partial of z with respect to s is t squared. Multiply the coefficients first. 2t times t is 2t squared. And then I've got sine of s times cosine of s. Multiply the coefficients here. I've got negative 2t squared sine of s times cosine of s. That works out. So those reduce. And here, t squared times t squared is t to the 4th. So partial of w with respect to s is 2s t to the 4th, which is exactly what we got when we substituted, so that's a very good thing. This is the answer for the partial of w with respect to t. Let's see if we get the same thing using the formula. So the partial of w with respect to t has 3 terms. We've got one term that has x's in it, one term with y's, one term with z's, and then we just substitute. Now you've already done those partials of w with respect to x, y, and z, so you can just substitute those again. So we get 2t sine of s, 2t cosine of s, and 2s t squared. And then the derivatives of x, y, and z with respect to t are on this sheet. Derivative of x with respect to t was sine of s. Derivative of y with respect to t, cosine of s. Derivative of z with respect to t was 2st. Now we just want to simplify. We've got 2t and a sine times a sine, so that's sine squared s. And a 2t cosine times cosine is cosine squared s. Multiply the coefficients. S times s is s squared. T times t squared times t is t cubed. And these guys have a 2t in common, so you can factor that out. And sine squared s plus cosine squared s is 1. That's nice. Always nice when that happens. So we get 2t plus 4s squared t cubed. Is that the same thing that we got the other way? Yes, it is. It's a very good sign. Okay. So these are our two chain rules for the partial of w with respect to s and t if w originally had three variables, x, y, and z. Since it had three variables, x, y, and z to begin with, your chain rules are going to have three terms. And if the new variables only have two variables, we've got two new independent variables. We're going from x, y's, and z's to s's and t's. The new w is a function of s and t only. So we want these partials with respect to s, or with respect to x, y, and z, written in terms of s and t by substitution. And then we take the partials of these guys with respect to s and t and multiply them in the appropriate way. Of course, this can be written in a shorthand, which looks much more like our Calculus 1 chain rule. It's the gradient of the outside function evaluated at the inside function, dotted with the derivative of the inside. If the inside function depends on two variables, it's a partial derivative of the inside with respect to the appropriate variable. If I want the partial derivative of w with respect to s, this needs to be the partial derivative of r with respect to s. If I want the partial of w with respect to t, this has to be the partial of r with respect to t. Or if you don't like using this shorthand notation, you can always use this expanded form. It's totally fine. And I think that's it. I think we've covered all the cases that you're likely to see in this class. So we did the first case when you have originally a function of two variables going to two new variables. Then we've got a function of three variables going to two new variables. And this is a function of n variables, and then we're going to two new variables. So we can just talk through this one. We probably won't do an example of it, but we'll talk through it. If w originally depended on n variables, x sub 1, x sub 2, x sub 3, all the way through x sub n, the partial of w with respect to s is the partial of w with respect to x1 times the partial of x1 with respect to s, plus the partial of w with respect to x2 times the partial of x sub 2 with respect to s. And you keep going. You had n variables, so you're going to have n terms. And if you separate this and you write it as a dot product, you'll see that it's the dot product of the gradient of w. So you're taking the first partials of w with respect to those n variables, x sub 1 through x sub n, and you're dotting it with the partial of x1 with respect to s, the partial of x2 with respect to s, partial of x sub 3 with respect to s, all the way through the partial of x sub n with respect to s. When I multiply these together, I get this. This is Leibniz notation, this is subscript notation, but it means the same thing. But this is the gradient of w, which is given by this function f, evaluated at x sub 1 of s and t, x sub 2 of s and t, all the way through x sub n of s and t. So this is the gradient entirely in terms of s and t. And this is the vector valued function r of s and t, but we've taken its derivatives with respect to s, treating t as a constant. So that is the partial of r with respect to s. Or we can use shorthand for all that. We can call that r of s and t. So this is the gradient of f evaluated at r of s and t. And we're dotting it with the partial of r with respect to s to get the partial of w with respect to s. Now, if I want a derivative of w with respect to t, I'm still going to take the gradient and evaluate it at all of the components of r of s and t. So this guy is going to be exactly the same. The only thing that will change is that when I'm multiplying by this other function, I'm going to take r, which depended on s and t, and I'll take its partial with respect to t. So everything that we've done just extends to n variables. Now, the two cases that we've discussed, we had a function of 2 variables to start, a function of 3 variables, and a function of n variables. And initially we took those functions of 2, 3, and n variables and went to a single variable, t. Then in this video, we took our functions of 2, 3, and n variables and wrote them as functions of 2 new variables, s and t. So I went from 2 variables to 2 variables, or 3 variables to 2 variables, or n variables to 2 variables. Now theoretically, I could go from n variables to m variables. I guess we could call them t sub 1 through t sub m, where there are m of them over here. And these chain rules could be generalized for that as well. But I think you see how they work. You're just going to see patterns like this, where you're taking the gradient of the outside function and you're evaluating it at this vector valued function. And then you're taking the derivative, the partial derivative of that vector valued function with respect to one of your new variables. When you dot those, you're going to get the derivative of the outside function, partial derivative of the outside function with respect to that new variable. And so if we had m new variables, we'd actually have m equations like this, and they would all look exactly the same. The only thing that would change over here would be these subscripts, because we'd be taking partials of the vector valued function r with respect to our m new variables. It sounds complicated, but if you can take a derivative, a Calc 1 derivative, you can take a partial derivative, you can do this. It's just a lot of bookkeeping, and you have to remember what all those subscripts mean.